All right, welcome everyone. Thanks for being here. So of course we're going to talk about microservices because that's sort of in the title of the conference, but specifically about data and how to deal with this this problem in the context of microservices. So my name is Emmanuel Bernard. I've been a committer on the Hibernate portfolio, like set of projects for quite a while, and others, but I'm the chief architect on the middleware side for data at Red Hat. Wait, is it IBM? I don't know. I'm very confused today. So I won't talk about the benefits of microservices. Hopefully there is conferences that are describing that today. What I like about microservices personally, and I really focus on, is the ability to develop a feature with a super high velocity and not having impact on the other features. So the ability to really have a very fast turnover from a business point of view and deciding, I need to spend all of my energy on that. It doesn't mean that as a throughput, you will be faster and deliver more, but it means you will deliver what is the most important right now. The other thing I like is the scalability aspect of microservices. So especially if you combine that with a automated deployment platform of sort, I'm in the Kubernetes/OpenShift world really, but the ability to say that specific piece needs to scale up quite a bunch or scale down and really adapt that is really important. So in that context, when you start a microservices project, either you're very lucky and start a new company and start from scratch, or you have existing applications and for sure existing data, and you're starting to build new services on top of that data. So that's the first part of that presentation is, I forgot to introduce you. Sorry, I'm not going to be alone. Here there is okay. Madhu, sorry man.
Thank you. So my name is Madhu Coulibaly. I'm a solution architect specialized on the cloud native development at Red Hat, so especially on our platform OpenShift.
Okay, sorry man.
Thank you.
Yes, what I was saying. So how do I consume this existing data into my microservices universe? So remember, so here I represented a split of one big old application into 5, but let's imagine the ratio is more like 1:20 or something like that. So what we like is that each feature can be redeployed independently, very fast and in isolation from the rest, right? But when you bring the data, when you have one application that is split into 20 or even more, it's very likely that the same data somehow will be reused in one shape or another. After all, a customer is a customer is a customer. If you do booking, booking, rooms, all of that might be reused by more than one microservice. So you have to share the data. So one option is to say, well, I will keep my big ass database and all of the microservices will actually talk to this one database. You can. The problem is that you're not quite fully independent anymore. What's happening is, say, application 1 is actually dealing with the user, and application 2 is also dealing in some shape or form with the user. If I change the user table because I want to enhance the experience, maybe not only am I affecting application 1, but also application 2, which means instead of having independent lifecycle, I've got somewhat of a correlated lifecycle. The other problem is more let's say I'm optimizing application 3. I'm adding a new index to really get stuff going. The problem is maybe my index, which is optimizing me, application 3, might make the application 5 10 times slower. So that's not really perfect to say, let's put everything under one database and deal with that in that fashion. The target model really in the microservice universe is each service is really an island of both the execution and the data. And this is the piece that has to be somewhat isolated from a lifecycle point of view, so that I can redeploy a new version over and over without affecting the rest of the other islands of my application. Okay? Martin Fowler has been famous for trying to crystallize and explain into words this concept. But of course, the islands, one way or another. So the islands have to communicate, and those bridges can be data streams, for example, or actual data copy. I'm not sure if we can think for the mic or maybe shift the mic. Okay. Okay. Yeah, maybe do the data copy. Bridges are actually specific contracts that have to be very well defined, maybe have a schema, and this contract has to be not cast in stone, but very important because that's how you isolate your various microservices. Unfortunately, it's hard to reach that point because for people that have done domain-driven design and bounded context, did you manage to define your bounded context in the first time without making mistakes? You know, I don't. So those boundaries might change. So when you move your monolithic database data into those microservices and you made mistakes, then you still have to shift stuff around, which is not quite nice. Also, your monolith application, it cannot work anymore. The whole database holding all of the state is gone because you've split everything out, right? So how do you work around that? So this presentation is going to be about options that we offer you, things we've been working on with. You don't have to accept them or embrace them 100%, but it lets you think about those subjects. So one option is to use data virtualization. So data virtualization is essentially, from an application point of view, it really looks like a database. So I'm writing so I've got my monolithic application, my monolith database, and I've got new microservices here. And those microservices, they don't talk to the monolith database really. They talk to a virtual database. A virtual database has an endpoint, just like a socket open, listening to whatever SQL queries and requests you're asking. You talk to it in JDBC, ODBC, whatever the connection strategy you're using. But the virtual database has a logical schema, which is for the new registration app, very centered around the user and probably not about orders or booking or whatever. And that virtual database doesn't store any state. It actually delegates and asks the state to the actual main database. So it virtually isolates as if it was an independent database, but it's not, or at least not yet. Okay? So what are the benefits? The data remains centralized, which means my monolith application still works. So I can start adding new services and slowly deprecate pieces of my monolith application without breaking everything. So that's an interesting step. The other step is that it really enforces the clear boundaries between each microservice. If a microservice wants to access another table explicitly, yeah? Okay, I'm ready to go. Lots of challenge today. Yeah, monolith still works. Yes, I can really define the boundaries, and it will be an extra step for the team to say, hey, instead of just using this user table, I will also want to use this extra table. You're going to have to go through and redefine at the logical mapping this extension. So it's a very clear expression of things, instead of just slightly saying, oh, I'm just one step away from this extra table. Let's just do it. It's going to be easier. And then you hold up with a big monolith again. It's read-write, which is very important. Any change you do at the microservice level will be visible on the monolith application, so that's quite interesting. And it really lets you prepare, work on your boundaries, the bounded contexts, and virtually make them, change them, and once you're ready, you will actually be able to do the actual data migration. Another one quickly is about evolution of one given microservice when it's using a database. So you got the V1 of the application, it's a code deployed and then a main database. Okay, I want V2. So if V2 is just about code, that's easy. If V2 is also about data changes, like new columns, maybe new tables, maybe updating the table structure somewhat, then it's a bit complicated to keep V1 and V2 somewhat backward compatible, right? And decide, okay, I'm rolling back V2 or I'm rolling forward things. If you add a virtual layer again, you can say, okay, my V2 is talking to the new schema, and then fall back to the main database for the existing state. And if you have specific artifacts, you might even also decide to put them in a side database, and the virtual layer actually aggregate them as if they were just one database, doing even joins and whatever. What's interesting is that once you're happy with V2, then you will potentially collapse those two layers. So that's the nice part. The even nicer part is, we only have nice and nicer. The even nicer part is that if you're unhappy about V2, how hard it is to roll back. Well, I'm removing the V2 application, changing the AB routing, removing the virtual layer, getting rid of these extra artifacts, and I'm back in business. I haven't changed my existing database, which probably is somewhat big, right? So quite a few benefits. Data security is another aspect that you need to think about. You need to think about it anyway, but in microservices, because you have many more data sources and many more people wanting to go and access them, you need to be extra careful about that. Especially people, GDPR, all of that is also adding even more, legal and teeth to that concept. The one I'm interested in, I'm not claiming it's like the whole security needs, but the one I'm interested in is making sure that you only have access to the subset of the data you really need from a given microservice point of view. So in case there is some kind of leak or compromise, then this is the limitation that's happening. Maybe I want to anonymize the data so a given microservice doesn't see, credit card numbers or whatever. Maybe you want to say if it's an admin, it's got access to more things than if it's just the guy at the counter in an hotel or whatever, right? So deciding per role who has access to what. And of course, auditing. I know somebody read that stuff, I know somebody updated that stuff, and I want to be able to go back in time and say, okay, here is what happened during this breach or whatever. Hopefully it won't happen to you, but never know. So again, the approach is to look at data virtualization as a data firewall in this case. So your application, again, looks at the virtual database as if it was a real one. And on this virtual database, you define the schema you want the application to see, and that virtual database will actually go down and access the old database. Okay? And then you can add layers of security on top. Do I want role-based access control on top of this schema restriction? Do I want to audit everything and then push those logs into something like Elasticsearch for further analysis? These are options you can add to your system. By the way, the open source project is called te.org. There are other projects in this area. That's the one we tend to take care of in the Red Hat universe. So what I like about this is that from an application development point of view, from a microservices point of view, then it doesn't change anything. You're just connecting to a database with a JDBC driver or ODBC driver, and you're doing your job. But you can decide at this data firewall layer, what you want to enforce from a security point of view. You can even adjust that. You can have even a different team dealing with that, which is interesting. And finally, it can be the same technology spread across all of the microservices in a somewhat harmonized fashion. And I've talked a lot, so let's go and start with a demo, a bit of a demo.
Yes, thank you, Emmanuel. So the demo I'm going to show you in the moment is based on a hotel booking reservation scenario. So the original hotel booking system is one large application with one single database which contains all business logic, all call, all data, all information about booking reservation, customer details, and hotel and room inventory. So the problem is that we need to face in, let's say, three main challenges at the same time. The first one is about adding new features, new functionality to our application, and to be compliant with existing and new regulations. The second one is about tight deadline, because even the small change of one part of the application requires many teams to be involved, and we want that all the team will be able to work independently and in parallel. And the last one, and I think the most important, is about customer experience, because we want to have zero downtime. We don't want to impact our customer when doing maintenance and so on. And of course, to fulfill all these requirements, so we set up a microservice architecture. So this is the architecture of the demo that I'm going to explain step by step, and I'm going to explain you step by step how we build it. So first, let's break up the monolith database. So on the left-hand side, you can see the original application with one monolith database, which contains a typical data model. So not sure that you see, I mean, even if you don't see this clearly, I think you have an idea what is it. Several different tables, several different entities linked by IDs. You have foreigner key, primary key, and so on. So the first thing that we made is to create a virtual data abstraction layer. So with 3 virtual databases. So 1 database per microservices. And each of these data services, each of these virtual database is going to expose only the data needed for a specific domain. So you are going to have 1 aggregated table for a reservation, 2 for inventory, for the hotel and the room, and 2 also for customer, so 1 especially that we are going to use for authentication, and the other one to get all the details about the customer. But I think you have one question: what a virtual database look like? So for that, I'm going to show you here. So a virtual database, for example, here, the virtual database, it's an XML file with a specific syntax which is going to describe all information about the customer logic. So you are going to have, of course, so the name of the virtual database. Here you are going to have the source model. So here it's the monolith database, especially using a PostgreSQL. But just think that you can have several models of that with different kind of technology. In fact, because it's a data abstraction layer, so there is no problem with that. And then we define the virtual layer, so the data service layer, and we retrieve the definition of our 2 virtual table. So for the customer and for the details. For example, for the details, it's a free table join from the monolith database, which we have some data transformation. For example, here we concatenate the address with the city name and some data anonymization because we only display the 4 last digits of the credit card number. So once we create this virtual database, so we, of course, deploy them on top of a data virtualization server. So as mentioned by Emmanuel, so we deployed all the demo on top of OpenShift, our container platform. And we have the information here. Here is our virtual data virtualization servers. And I'm going to show you that the virtual database is going to act as a normal physical database because, for example, using a SQL client. So, for example, for the customer VDB that I'm going to screen here, so I'm going to edit just the connection. So from the connection, you can see that we have all the information about the DGBC connection, so the name of my virtual database, my OpenShift endpoint, and the user password, of course. And now on here, the tree, you are going to see that, oops, let me just disconnect and reconnect. Okay, you are going to see, in fact, at that level, you will be able to see that it really acts as a normal one. You are going to retrieve all the information that you need. Oops. The demo effect, as usual. Okay, now it's better. You retrieve your virtual, the data service layer, and then on table we have our 2 tables that we retrieve, and I'm able to issue classic SQL queries. So, for example, here when I concatenate, so customer coming from Kyoto and from Lima. And I'm going to use exactly the same way to connecting the data to my microservices. Because on top of that, of course, I'm going to create microservices which is going to read data from my virtual database. And on the microservices, so all my microservices that I've developed is based on Spring Boot application. And of course, on the application.properties file, you can retrieve all the information, exactly the same that I use for the SQL client, especially for the data virtualization driver, the JDBC URL, and logging password. Once I create my application, I deploy, of course, on top of OpenShift. So here I have my microservices reading data from my data virtualization. And we are going to make a quick test and using some Swagger to just query the information. So from my controller, customer controller, I go to get some information for a specific customer. I'm going to try out. Let's take information, for example, from Stella Strotzman. So 407, I execute my Swagger. And you can see that my microservices is up and running, and I retrieve my data transformation, my concatenation, and my data anonymization. So what we demonstrate here is how easy and how fast is to break up, so virtually, a database, and also to consume the data exposed by virtual database to microservices. And now we are going to talk about how we deal with state in such a context.
So we've been told to write stateless applications, but when you think about it, an application without state, it's not doing much, right? So it's just happened that we move the state somewhere else. I'll explain how to deal with it, but before that, why are we writing stateless applications? Because it's much easier. When you're in an environment, when you want to be able to scale up, scale down very nicely, if you don't have to deal with state, you just do kill -9, and that's how you scale down. And the effect on the user, providing your routing structure is decent, is okay, then has zero downtime, zero problem around that. But of course, you have to deal with state. So the question is, how do you create this magic unicorn, and how do you address that problem? If you say, no, I'm not writing my stateless application, which is simpler, I'll actually onboard the state inside the stateless application. And it could mean having a cache in it and having to deal with invalidation across all of those instances. It could mean something more than just cached data. It's hard, right? It's a distributed system, essentially. So having to deal with that adds a lot of complexity to your application and moves you away from, the business focus of your application. The other problem is that from a scalability point of view, you're scaling two things at the same time. The state, the volume of data you want in memory or somewhere else, and the CPU, essentially, the compute things. The other problem is, if you have a V1 of an application and then know you're working on a V2, do they share states if they happen to be handling the state in a somewhat different fashion? How can they share the state so that it's a seamless evolution from V1 to V2 from the user's point of view? And by state, I do mean it could be the long-term state that you would typically put in a database or an NoSQL system or whatever. But it could be something a bit shorter, like basket, the last n articles seen by a user. Maybe that state is actually reused to input into a machine learning model that will then provide live recommendation to a user. You can imagine lots of interesting things with this temporary or intermediary state. So again, that's an option. What we've been experiencing with quite a lot of success is working with a data grid as your state management. In this case, the open source project is Infinispan, but there is plenty of alternative solutions. Of course, that's not as good, but life is hard. So your application is stateless, and when they want to deal with state, they go and read that in the data grid or from the data grid, and they update it there. The advantage is if I add new nodes, V1 nodes, or remove them, it doesn't matter, they don't have any state. I can have V1 or V2 of the application share the same state and have a seamless operation. And what's interesting about data grid is that first of all, they keep most of their data as much as they can in memory, so the latency is actually just a network hop, which is getting better and better these days. And the other thing is it scales very nicely up and down. It has essentially a rebalancing characteristics of the data moving. So you add new nodes, the data is spread across all of those nodes, and then the load is somewhat evened. What if I lose one node? Let's say if you see in bold, I've split the alphabet into each of those nodes. By the way, it's not in range, it's more like a consistent hash, but it's a bit simpler to explain here. So let's say I'm losing node 2. The G2L data is lost because the node owning that is gone. That's okay because the backup was there in node number 1, right? And then the data is rebalanced and we find a new main owner and a backup, and life goes on. Yeah, I think that's what I wanted to say here. So the elasticity is very natural for those kind of products. They work hard to make that happen so that your application doesn't have to. So low latency, you keep the complexity outside of your application from a state management point of view. There is another one that I really like, especially in the category called the data grids. They have what is called cross data center replication, or even zone availability replications, depends how you call it. So it could be 2 physical data centers, it could be 2 areas, 2 racks, or 2 areas within a given data center. What is interesting here is that you will evenly split your load between one zone and another. Maybe you'll do user affinity. All of the users from A to M go to the first one, and then the other guys go to data center number 2. The advantage of doing an affinity here is that all of the compute for a given user remains local to that data center, so you don't have cross data center communication all of the time. But what the data grid does, it actually synchronizes 2 data grids with one another, so it's fully replicated between those 2. So in case you do lose a data center, you can fall back to everybody to the second one without loss of data. And that is automated for you, so that's quite interesting. There is a very nice pattern if you do that. So data grids can detect conflicts and do merge resolution strategies and whatnot. But what we recommend is exactly what I was saying. Do a customer affinity so that all of the state, all of the data for a given customer is always read and written from one given zone at a given time. So that all of the writes are actually propagated in one direction for that given user. Which means you don't have any kind of, you've got less state management and state conflict management to deal with. So caching, it looks like caching, except we don't want to lose state, right? Remember, we actually replicate the state. So we pay in memory to save, to not lose our state. Caching, you don't care if you lose state, you just want it to be fast most of the time. And why do you want it to be fast? Well, in a microservice, instead to do one feature, you tend to have to go and call potentially several microservices, sometimes in a row, which means you add latency. So if each microservice is fast, you reduces the problem here. Another one, if you lose one service and somehow whatever the service was providing is cached somehow before that, then you might be able to have a degraded mode, but still being able to serve some of the most commonly requested requests on that. How to do that? Again, you can use a data grid. The main difference here is that we don't duplicate the state into more than one node, because here what we're interested in is to cram as much data as possible per megabytes of memory. Okay? So if you lose one node, well, your data will be slower until a node comes back with whatever hot deployment technology you have. So in our case, it's Kubernetes OpenShift. And then the node comes back, and then it's ready to accept new state and do its caching thing. Another advantage, when you look at it from a consumption per megabyte point of view, is if you were to do a local cache at each instance of the application, your hit-miss ratio would be less efficient at the same amount of memory used for caching, because each application will say, okay, country France, very commonly used, country something else, Vatican, not so commonly used, right? So the hit-miss when I'm hitting Vatican will be probably more of a miss than a hit, because I'm limited in memory per instance of the application, right? So I'm replicating a lot of the data per instance. If I have a shared cache strategy, for the same amount of memory, I do have a better hit-miss ratio, because Vatican will be shared by all of the applications there. Make sense? Well, if it doesn't, think about it and then ask me questions. Finally, we've talked about going from a monolith database and slowly going your way through the microservices. We've talking about these temporary state and how to speed things up and the interesting patterns into the microservices. What happens when you're mature and you want to move, one step further? Remember this diagram where we had these islands of microservices. I told you it's hard to achieve that. It's true, but once you're there and once you've very nicely defined your bridge contracts, whether it be data streams, whether it be actual data copy like ETL style, but at least very well defined, then you gain a lot of flexibilities. So first of all, you're able to add new microservices that consume the same data very easily. So I've got app 1 that is saying, hey, I'm generating data with this contract. Whoever wants to consume it, go consume it, or within rights, right? So application 2 was the initial consumer of that, but maybe I want to write application 6 that will read the same data, maybe do some machine learning model generation based on that, so that I can then feed that back into my application. That's a new area, new application, that I'm consuming the same data. So you can very easily add a new features. You can also decide, I'm going to have a V2 of application 2, and I will consume the same data from the same data stream and have them, bad choice, but app2 v1 and app2 v2 running in parallel off the same feed, do some, let it live for a while, and then decide when you want to do the switch. On the scalability aspect, I'm going to re-explain something I explained, but because you got something very focused, you will be able to say, look, my scalability concern is for the app 3 part of things. So I can literally say to the team, destroy it and rewrite from scratch and have something that works at scale, right? Because that's the area where we are having trouble. Not app 1, not app 2, not app 4, not app 5. Those don't have to change. If it were in a monolith model, you would have to rewrite everything, especially if you had to change the underlying data structure, like from relational database to, I don't know, Cassandra or whatever, right? That's a big rework. Whereas here, you actually can minimize the effort. I won't talk much about CQRS. I'm sure there are other presentations here going to detail that. But what's interesting about CQRS is, for people not familiar, is the separation of, here is the operations I want to do from a change point of view. So that's the command. And then, so it's command, query, request, segregations. Segregation meaning separation, right? And the request is essentially the views you want to expose for that data, for that service. And you can think of them as one microservice for the command resolutions and one microservice for each of the views I want to expose and be optimized for my system. So it looks very much like that kind of model. A typical solution to use in those universe, especially in the data stream model, is to use Kafka as the events you will keep in a Kafka queue and keep forever and be able to replay somehow. To help in that area, there is the notion of change data capture. There is a project called Debezium that is built on top of Kafka and Kafka Connect today. And what it does is it looks like at the database, look at the context, the log, transactional or not, right? Let's say the transactional log. Look at the changes that are happening and create an event for each change that is happening. Hey, I've changed that column. Hey, I've added this new row. Hey, I'm deleting this entire table or whatever. You've got a list of changes that are happening in a queue, stored in a queue. And then I can have applications that will consume those changes and do work with it. Maybe I'll start with this microservice at the bottom that will, is only interested about the monetary area to then push some notification to the user saying, hey, you've had an operation on your account or whatever. So I don't care about a lot of the data, just that for a given user, I want to push that to the user. The other service is more of an aggregation, but again, by reading the diffs, I'll be able to rebuild the states, especially for that microservice, and consume it. If you're interested in Debezium, you should have joined the workshop which is Wednesday. So I don't know if there is still time to move around, but we're gonna discuss that in much more details. But what are the benefits is you really decorrelate the notion of here is the changes that are happening in my database and here is how I consume it. So not every application has to read the same database. So you save in the load for that database, right? Because you just read the changes once, it's in a Kafka queue, and then you can replay it and re-execute it, but from the Kafka point of view on, without affecting the monolith database. So it's a nice way to say I'm going to scale my system, adding new features without affecting the existing one. And the other thing is, it's much more real time. Instead of saying, okay, I'm going to read the database every 24 hours or every 3 weeks and do something, here you literally have events coming up. So you can really have a real-time-ish effect over time on your system. So a quite interesting benefit of change data capture. Again, Debezium is an open source project. You can have a look at it. Debezium.io, if I'm not mistaken.
Yes. Okay. So let's continue on the demo. So previously what we have on the demo, so we prepare three microservices reading data from the virtual database. And of course, the next step after that is to create a web application on top of that. So now that we have the web application, let's start to booking a room. So what I have here, so what I'm going to do, let's say that I'm in the public transport and I need to book a room, for example, for my next vacation, and I'm going to go, for example, to Lima. So what I'm going to do is I'm going to connect to my application, then I'm going to enter my credential. Oops, sorry. So Cheska@yahoo.com. My password. Okay. So now I'm inside my application. So let's start booking a room. So I would like to go, as I mentioned, to Lima from the 5th, so November 5th to November 18th. Let's say like this. So I submit my information. So here I have the list of all the hotels available from this period. So let's say that I'm going to use that hotel, the Lima Park Terrace. So I'm going to select that. Here I have the list of the room. And now I need just to stop because I arrived to my train station or I have a call or so on. So let's say that here I'm stopped in that part. In the meantime, what I'm going to do, let me just refresh all of them. What I'm going to do, I'm going to kill all the instances of my application. So I'm going here, I'm going to kill all, so microservices instance and my web application. So I kill them all. And what it's going to do is that because my platform, it's automatically inherited by my platform, because I killed the process, my platform is going to reput them. So it's some capability that we have with OpenShift. And let's say at the meantime, so I arrive at home and now I want to finish my booking state. So let's wait that all my microservices just come up again, and then we're going to continue the booking state from a web browser. The last one, which is awesome. Okay. So now what I'm going to do still from my OpenShift platform, I'm going now to connect using the browser. It's coming. Yes. So now I'm enter my credential. I'm enter. And now you can see that I have a notification saying that I have a booking in progress. And of course, when I click on this part, so I'm able to continue my booking process where I left when I was in the public transport, in the train, and so on. So I think how it's possible. So I think you have an idea about how it's possible, because of course, my microservices and my web application are completely stateless. And all the process and all the steps that I make during that process, I share it, I store it into my in-memory database. And of course, for the in-memory database, we explained that how it's possible, for example, to scale it, to scale down. So it's really simple, because from the application, so for example, I'm able to add 2 new pods just by clicking like this. It's going to reboot that pod directly that instant. But let's go further. Let's say that I would like now to be able to test a new version of my application. So if you can see here, so from the route, so here, all the traffic is going to just my application that I have here. It's my first version of the application. So what I'm going to do, I'm going to redirect 75% of my traffic to my second version of my application. So basically, I'm going to use A/B testing. So 75%, so I click on that. So now you see that I've changed with the 75% from the application V2. What I'm going to do very quickly is go back to my booking. So now I would like to go to Marseille from 12 to 12, so in December. I submit the information. I'm selecting one hotel, the Marseille 7th place, and now I'm the booking. So as you can see here, I have exactly the same version of my application. And if I go back to my mobile, it's just to show you that it's not stored into my browser and so on. So I go back to my mobile. From my mobile, let's go back to the overview. So you can see here, I still have my notification that I have a booking in progress. And when I click on resume, as you can see now, I have a new view where I highlight all the rooms which contain a living area. So basically here I have my living area here, and here I don't have any living area, so it's not in green. So here, what we demonstrate, especially for these parts, is the way that we are able, as mentioned Emmanuel, to have the same state, to be able to share them between different microservices, different applications. So here the web application. And it's also possible to share that state between the same version of the application, which is going to be able to use some A/B testing, for example, and also to be able to upgrade the application without downtime, so to using some routing and capability of our container platform. So now I will let Emmanuel for the final word of the presentation.
We've been a bit chatty, so I'll go fast. So these are options. It was for you to think about the problems you're having in your microservice architecture and maybe choose one or the other, or maybe rethink some of your strategies. This notion of being able to move slowly with the virtual database, we think is a very powerful concept to really get your toe into the water and not breaking the past too fast. Try and keep your application really focused on the business and delegate the hard part of state management essentially to a system, whatever it is, right? And have it be native to your platform that is able to scale up and down and whatever. It's going to be easier for you. And yeah, of course, microservice is a journey, not just like, hey, from now on I'm a microservices shop. No, it doesn't work like that. I'm going to skip that. These are the references from what we've been describing. The code is there. There's an interesting book about how do I make my relational database evolve over time with backward compatibility in mind. There is a bunch of patterns right there. It's a small book. It's free, 50 pages or something. Very good. And a few blogs around those strategies. And let's open up for a few questions, if you have any.
So anyone has question?
I can't believe the French crowd has no question. There you go.
I have a question with when you show that you can create a virtual database
Yeah.
and make a concatenation, you concatenate two fields. How does it work when you have a write operation? How will you
Okay.
split that back?
So I'll repeat the question and you will answer it. So the question is, we've seen a view where we actually modified the data by doing concatenation of two fields into one. And I said in another slide that the view was read-write. So how do you solve that problem?
So yes, so basically, in fact, it's how the definition, how you are going to write into a view, especially in virtual view. So with data virtualization, it's a bit like the secure RS pattern. So way is that you need to have one definition of how you read the data. And after that, you create also a special, let's say, definition to write the data. Because underline, it is some physical table, real table, and you need to map, let's say, your view and the information that you have to your view to say exactly what is going to happen and to which data sources is going to have this read. So it's really just a separated way, a separated really definition of that view.
So of course it has to be a non-destructive thing. So the credit card wouldn't work in that situation. So you would not allow for the writing of the credit card. Another question? Okay. Well, thank you very much for being there, and have a good week.
Thank you.